talking about consistency statements in bounded arithmetic.
Thank you. I like to be introduced and not to introduce myself. Maybe in some years that will be different. Right, so I want to speak about a problem which I was thinking about off and on over the years and now picked up again, and which is probably not that known. So it's about how to make use of or whether consistency statements in bounded arithmetic can be used in order to to answer questions there. So let me remind you what bounded arithmetic is and what the history of consistency statements is there. So I don't want to formally introduce bounded arithmetic, but just draw a picture. So let's say first bounded arithmetic. So bounded arithmetic, these are sub-theories of arithmetic, of Peano arithmetic. They were introduced by Swansea, at least in the way I will introduce them here. So you have certain theories S12, S22, S32, and so on, which form a hierarchy, which correspond in some way to computational complexity classes, namely complexity classes of functions. So these correspond in some way to the polynomial time computable functions, these to the second level in the polynomial time hierarchy of functions, these to the third level, and so on. So due to these correspondences and due to some other theorems, the main open problem in bounded arithmetic is to separate theories. Yeah, so is it that any of these levels are separated from each other? This is supposed to be a very complicated problem. At least it's open for 25 years, and there are some connections known to the separation problem of complexity classes. It's not exactly that if you get a separation here, you get a separation there, but okay, so in words it is that so the hierarchy of theory collapses if and only if let me get it right. So the essence is the hierarchy could be separated, but the complexity classes could still collapse, but then the collapse must be so complicated that it is not provable in bounded arithmetic anymore. So that's the thing which you get here in the connection. So if the bounded arithmetic hierarchy collapses, then complexity classes will also collapse. If this is separated, then we know something about how complicated a possible collapse of complexity classes must be. So nevertheless, people think, well, even though we do not have really a strong theorem which says that they are really equivalent, people overall think that they are actually equivalent. So once you are able to separate theories, you may have enough tools and information in order to also separate complexity classes. Okay, so that's one thing. And now, so if you just think about theories and not about complexity classes, then of course a natural way of attacking this problem is to look at consistency statements. Yeah, use Gödel's second incompleteness theorem, try to express, so you can formalize it here for theories of bounded arithmetic, so you get a statement which is not provable in the theory, try to prove it in some stronger theory. So that's the second part, consistency. So let's take as a first statement, con of t as the statement there is no proof of 0 equals 1. How precisely do I want to have it? In predicate logic, from T. Yeah, so you take T as a set of axioms, you allow predicate logic in general, and then you formalize in the standard way, in some standard way, that there is no proof of contradiction of 0 equals 1 in, from these axioms. So I always bothered with, I'm always interested in theories of arithmetic, so therefore 0 equals 1 is fine. So let's say you have always some basic arithmetic in there. Okay, so this is a very strong notion of consistency. Already Paris and Wilkie showed. Oh, maybe I put this here. And I think it was 87. That you cannot prove the consistency of Robinson's Q in the theory I delta 0 plus exponentiation. Yeah, and this shows, if you translate it to theories of bounded arithmetic, you get, because I delta 0 plus exponentiation contains everything from bounded arithmetic, so if you take the whole of bounded arithmetic, this does not prove, well, then take as let's say -1, 2, where as -1, 2 is here at the bottom, you simply drop all induction axioms and just have the theory consisting of the non-logical axioms which axiomatize the symbols in bounded arithmetic. Yeah, then that contains Q as well, so you know, okay, this notion is so strong that if you take the consistency of its weakest fragment, it's not provable in bounded arithmetic anywhere. Okay, so then people started to somehow weaken this predicate. For example, you can consider bounded consistency, where I take the same thing, but say that where all occurring formulas are bounded. Yeah, and bounded means, so all quantifiers are bounded, so a numerical quantifier is bounded by some term. That's, of course, now you restrict the class of proofs at which you are looking at. Yeah, you only allow proofs which where all formulas have to be bounded, not unbounded quantifiers anymore. But it could also be shown that this is too strong, and I think the final result was by Pavel Putlak in 1990, who showed that S2 does not prove the bounded consistency, and I think it was on the first level. Yes. Right, so this is a little bit of the history, and somehow here one gets the feeling that, okay, consistency statements are too strong. Even if you try to weaken them, you are still not able to prove anything, and to prove them anywhere in bounded arithmetic. And somehow the strongest theorem, which I want to mention here, is due to Bas and Ignatowicz. Which goes as follows. So it works with a version of Cook's system PV. So you consider as the language all functions, symbols for all functions which are polynomial time computable, and you take as axioms their recursive definition. Let's say you axiomatize them as Cobham's class using some algebraic schemes like composition and limited recursion and some basic functions. So you take their recursive definition according to these schemes, plus some additional, so plus some finite set of further axioms. For example, you will have subtraction, arithmetic subtraction in the language, and you want to, besides its recursive definition in some way, you also want to say that a minus a is 0. Something which you, if you just have the recursive definition, would have to prove by induction. But we want to get some theory which doesn't contain induction. So you have to add a certain amount of additional axioms. Formulas are built by using equality, inequalities, and Boolean connectives. So I'm describing now the language, formulas, and what are the proofs which we are allowed. So the lines in proofs are given by sequence, and the rules which we allow in the proof are first rules for equational reasoning. Yeah, the typical, so you have an axiom stating a reflexivity, and then you have rules for symmetry of the equality relation and transitivity and compatibility with function symbols. Plus, okay, the other things are these propositional connectives. So you also allow propositional, Genson's propositional LK rules for this. So this is the proof system which you're looking at. And then they are able, so no induction is given there, so it's just some function algebra, mainly the recursive definition plus some extra axioms, and you allow you a little bit of reasoning, so to make things a little bit easier to write down, so that you have this propositional AK around this. And then what they are able to show, the theorem here, is that even in this theory, in S12 at least, you can simulate somehow Gödel's incompleteness, Gödel's second incompleteness theorem, and show that S12 cannot prove the consistency of this equational theory.
PV minus? What's PV minus?
PV minus. PV usually comes with induction. So this thing which is here, this is PV minus. This proof system is PV minus, without induction. The main thing is that you do not have induction there. Right, so on the other hand, you can show the following. That's the third part. You can actually prove certain consistencies, provable consistencies. And that's a theorem which I proved a while ago. It was in 2002, published in 2002. Namely, Takeuchi, based on these observations, formulated a conjecture where he said, okay, take the language of bound arithmetic and only the equational theory for the function symbols, where you only allow the recursive equations as axioms, and you're only looking at closed terms. Show that this theory, that the consistency of this theory cannot be proven in bound arithmetic. And this, actually, I showed that this is not true. You can, for such weak theories, you can actually prove the consistency. And it can be done even a little bit more general. So if you have F, some set of recursively defined functions, axiomatized axioms are only recursive definitions. Yeah, so you can have a recursive definition of arithmetical minus, but you do not have the statement a minus a equals 0. That would be something which you would have to prove by induction. That's not allowed. Formulas and lines are just equations. Yeah, we are now in a pure equational setting, not one where you allow a propositional k, and rules are just the ones for equational reasoning. Very much the same as in this result, only you drop the additional axioms and you are in a pure equational setting. And then you can show for any such set of function symbols that S12 proves. So let's call this theory here equational theory of F. Yeah, S12 can prove the consistency of this equational theory. In particular, and first, you can, for example, take a language where you can describe all partial recursive functions would work here. Yeah, if you just allow the recursive definition of them, you would still be able to prove the consistency of this equation theory in bound arithmetic in S12 in the first level. Or if you take this language described over there, if you just take the functions from PV minus without their additional axioms, and in this pure setting, you get that it is provable.
Can you say again what the difference is? So particularly you've got for PV minus, you've got the equals and the inequality and the conjunction. So you don't have those in the bottom.
You don't have this in the bottom, you only have equations.
Okay. And you said for the top one you've got equation reasoning plus something.
Plus propositional LK.
So that's for
so you need
conjunctions.
Rules, of course, for defining all connectives.
And equational reasoning is just rules about substitution and things like this.
Yeah. Okay, substitutions actually in both settings not included, but probably could. Right, and now so this is the point where I somehow always thought, okay, now we have these two things, which are very close, and actually, so what are the problems now, which I tried to look at? Well, as Bast and Ignatovic pointed out, you can actually arithmetize equations, equality, and propositional formulas, again, in equational logic. So if you do this, then, and if you then translate their proofs into these arithmetized proofs, you only get a polynomial blow up. So they claim at least that this is not a restriction. You can do the same thing as they are doing in a pure equational setting. Yeah, and so what does it mean? It means, so Bast and Ignatovic follows, from this follows there exists a set of axioms, let's call it X, such that if you add this set of axioms to the pure equational setting, let's say so in particular we have here that S12 proves the consistency of the equational theory which comes from, let's call it pure PV. Yeah, you take as pure PV only the recursive definition of the function symbols in PV, nothing else, not the additional axioms. Let's call this pure PV. So S12 proves this equation theory, and if you arithmetize their propositional, somehow more general setting where you have equality, inequality, and connectives, propositional connectives, then you get that probably you get a set of axioms such that which support this formalization, so that their argument still goes through you can somehow simulate Gödel's second incompleteness theorem. So you get there that S12 does not prove the consistency. Well, if you take the equational theory where you take pure PV plus this finite additional set of axioms. And now the natural foundational question is, okay, what is this set of axioms? So what do you actually have to do? Which function symbols do you need in order to formalize somehow, to arithmetize equations, inequalities, and formulas within a pure equation theory? And then can you narrow this gap? Yeah. So here you have a finite set of axioms how does it actually look like? And here, if you don't have it, then it is provable. If you add it, it becomes unprovable. How does it look like? How can you narrow it down? Yeah. So that would be one main problem which I tried to think about, but so far haven't achieved anything. Others, or a more concrete one would be, well, you could look at Bas and Ignatovic result and really try to minimize the set of additional axioms which they use there. So minimize additional axioms in Bas Ignatovic. And maybe a third one, to have a more concrete one, is whether one can extend this result here to a more general setting. For example, where instead of just looking at pure equations, you allow also equation reasoning plus propositional LK, but no additional axioms. Are you still able to prove its consistency in S12? So for example, extend to equational reasoning plus propositional LK. And anything which somehow would close, so in general I would say what I'm interested in is closing this gap between this between these statements or equation theories which make consistency unprovable in some weak, or where you can still carry out in some sense Gödel's second incompleteness theorem, and those where they become so weak that the consistency becomes provable, and try to narrow this gap by try to also add further axioms, maybe some axioms to this theory, and drop other axioms from the other one and see how close you can get. So maybe this gives you a picture of something important. I don't know. Thank you. That's all what I wanted to say.
Any higher levels of bounded arithmetic prove the consistency of PV minus?
What do you mean by higher levels?
S2
Beyond
S2.
S2?
No. S3, you say S12 doesn't prove it. What about S22, S32?
Yeah, okay. I think nobody looked at it, but I would assume they are also not provable there. But I don't know.
Well, I guess mine was the same question, really. Whether you can get anything for the higher levels.
Whether you can get anything in terms of probability of this statement, of this one.
Or the bottom one. Well,
or the bottom one. Some similar thing for higher levels.
Consistency statements that could separate higher levels in this way.
I think it has also Bas and Ignatovic haven't looked at higher levels, so whether you can do something similar. So what they do in order to get this result, they somehow start with a usual way of formalizing, or usual way of using Gödel's second incompleteness theorem for PV, and then try to get rid of induction. And they do this by somehow using the functions which you have in the language to somehow formalize a speed up of induction argument, a typical one, where you somehow use binary search in order to halve an interval. And if you iterate this sometimes you somehow can get rid, you can prove enough induction without induction, yeah? So just because you have narrowed it down to a constant interval somehow. And probably this can also be done for higher levels, I would assume.
But for the bottom part, if you start adding more induction than S12, is there some more things you can prove about your theory?
Still looking at the same theory?
Well, is there some way
I don't know.
the theory?
So this would mean that you somehow enlarge this thing and then, I don't know. You also had a question? Was there a question over there?
It's a similar question to Neil, but going back to the director. Do you need the full power of S12 for this? Can you prove it in PV? The full PV?
You should be able to just by conservativity.
Yeah. By conservativity, it depends on how this is formalized, right? So if you formalize it as an equation, then by conservativity you must also be able to prove this in PV, yes. I would assume no, but I never looked at it from this point of view.
I didn't quite understand your first question, Arnold. So you're saying that from their paper it follows that there's a set of axioms?
No, they claim in their paper that this looking at this more general setting is not a restriction, because what you can do is you can arithmetize equations.
Mm-hmm.
Yeah, so so you want to arithmetize all formulas which you have in the language by so that you can reason about these again with equations.
Mm-hmm.
So, for example, if you have done this for let's say for atomic formulas, then you could say that A and B goes to a term TA times TB, and this is true if and only if this is 1 or something like this. Yeah, so you can try to arithmetize all your formulas and then transport the whole proof via a translation into a pure equational proof about some terms being 0. This, of course, needs some further symbols in order to do this arithmetization, and some further properties which you have to state.
Mm-hmm.
But I think it's plausible that this is possible, and that you end up with some finite set of axioms which you need for this arithmetization, plus all the axioms which you already had, but no induction. So what you get is a finite set of axioms in, let's say, still the language PV minus, such that if you add these axioms to the proof theory, to the pure equation theory, then it becomes unprovable. If you drop this finite set of axioms, then it becomes provable.
So your question is to substantiate the claim that
Yes.
Okay.
Pin it down, write it down, the axioms, and then try to get it minimal and see whether there is actually some kind of barrier, something where you see, okay, this is a small set of axioms which somehow make it very complicated, everything else is handleable. And then
And the difficulty is it's just a lot of work, or it's just...
Mm-hmm. So far I try to write it down by hand. Mm-hmm. So if anyone knows a nice write-up of arithmetizations of formulas, then that would be something which could be a nice thing to look at for me at the first step. So I tried it on my own and simply gave up at some point. Yeah. So if anyone knows this being written up, I would be interested to know this.
One more question. So going back to your initial motivation to separate those theories, so I thought that you wanted to get some kind of statement, maybe some version of consistency that would be not provable in some weak class and provable in some stronger class that would separate those classes. So what you ended up with is kind of you have the same theory as 1, 2, but stated 2 different statements.
Mm-hmm.
One is provable, one is not. So how does it relate to your initial motivation?
Well, my belief is that the moment you try to somehow strengthen this thing by putting further things into the equation theory, you may have to go up you may have to go up into in levels of boundary arithmetic. So then you would end up that, okay, some version here becomes only provable in some higher level of boundary arithmetic, where okay, if you weaken this, it's still unprovable in first level. I'm not claiming that this is actually possible, or maybe at some point you really shoot again beyond boundary arithmetic, but still I find it worth knowing what is this thing, how close can you get it, and what makes it, okay, what happens there. Yeah.
Thank you.